Good afternoon, everybody. We'll get started in just a second. I should introduce myself. My name is Adrian Jackson. I'm from EPCC, and I will briefly share my video so I can say hi. I won't share it for the majority of the time because then I won't be able to keep my nose in peace. So I wanted to say hi before we started. I'm just going to wait a minute or two, and then we'll get going on this afternoon's Python continuation from the various materials that may be interesting to you if you want to use Python for high performance computing or computational simulation stuff. Okay, so I've just shared my window to highlight what we're going to do this afternoon. This afternoon is split into two parts. The first part, we're looking at the Numpy library and how you can use the Numpy library. So in contrast to Pandas this morning, something which is similar but different is Numpy. I'll go through how you use that. Then after the break, we will be looking at MPI for Pi, so how you use message passing from Python. There's a slight wrinkle in our lovely plans here today, in that the system we want to run the MPI for Pi stuff on Archer 2 is not at the moment working for compute jobs. There's a network problem with it. So we can get onto the system, we can go onto a login nodes, and we can run Python there, but we can't do any of the any of the MPI for Pi examples yet from after a break. It's unlikely that will change between now and when I start teaching the MPI for Pi stuff. So the plan for this afternoon is I'll go through the material, I'll discuss it with you, but then you'll have to come back at a later date. The machine should be up and running again by tomorrow, definitely. Come back at a later date and try out the practical bits yourself. And then if you have any questions or problems, you can then get in touch over email with myself, and I can help you out with those kind of things. Now, the nice thing is that these accounts for Archer 2 that you have, I'm hoping you've had set up yourselves, should be around for a couple of weeks, possibly even up to a month from now. So there should be time for you to get on and run through these practicals and experiment a little bit as well. So apologies for that at the moment. It's slightly beyond our control, my control at least anyway. So there was a hope it would be fixed this afternoon, but haven't quite got there yet. I've just had a message asking if I can speak louder, so let me just check I'm using my correct microphone here. Okay, so Gavin, is that any better for you? Okay. Right, so I've highlighted here what we're going to do today is, or this afternoon, is go through the NumPy lecture. And if we can get there, if we go to the training page for today, the data analytics using Python page, post materials location, and then down at the bottom here, there's two notebooks, NumPy Jupyter notebook there, which we'll do now, and then the MPI for Pi Jupyter notebook here. Now these are not notebooks which you can edit live. You'd have to run them locally to do that. But the idea is that you can look at the material I'm doing and then do it yourself in a terminal or in a window in a Python interpreter. But you can read the material that we're going through here. So I'll put this link that we're using today into the chat so that you can get it from there if you don't have a link directly through the Archer web page. But you should be able to see that here we have, we can ignore the logos, we have the whole lesson that we're going to do today, from setting up and introducing NumPy all the way through to saving out the data and looking at NumPy performance with some exercises you can do further down if you would like. So ideally, you have this web page open so that you can run through it alongside me. And then if I'm going too slow for you, then you can go ahead and look at the examples yourselves. And if I'm going too quickly for you, then do let me know. Do let me know where what if you have any questions, or if you would like me to slow down or repeat anything or anything like that. Also, if you need this screen here to be made bigger in size, I say that that's perfectly fine. Actually, what I'm going to do is in a minute, I'm going to stop sharing this web page, and what I'm going to share is my terminal instead on the Archer computer, so you can see live me typing these commands, which hopefully you're going to be able to do as well. Ideally, we would run this on Archer so that you have a feel for the Archer platform, and so that we can iron out any problems you have accessing Archer 2. I keep calling it Archer, but it's actually the Archer 2 service. The Archer 2 system before you come to do the MPI for Pi stuff yourself later. So if you've been given an Archer 2 account, or should I say, if you've signed up for an Archer 2 account, it would be great if you could log into that now and get something up and running where we can play around with Python there. So what I will do is I will show you my SSH window, my terminal on Archer at the moment. And let me have a look at that. So hopefully this will come up here. Now I can change the text size if it's not going to come up well as well. Let's have a look at that. I'm hoping that this should be reasonably visible for you. And so this is my terminal where I'm going to do my typing of the commands, which are on the web page, which you can follow from the web page from here. Let me just exit this Python. Let's see if we can play this. But hopefully you were able to log in to Archer 2 with your account. If you've been able to log into Archer 2 with your account, you should see some nice ASCII art, and then you should get up a command line which looks like this. Now, of course, my name is Adrian J here. Yours would be something else, but other than that, this should be what you have available. And then when we're on this system, what we can do is we can use this command here, module load. And we're going to load the Python module. Again, I'll put this into the chat, so you don't need to. You can copy and paste this if that's of use. And let me put this into the chat here. And this sets up the software so we can use Python on this system. So it's not doing anything special. It's just the way that software is often managed on large-scale systems like Archer 2. We have a set of modules where you can load in different software packages and use them. And indeed, we can have a look. I've got a whole bunch of modules loaded. When you actually log in, there's a whole bunch of software set up for you, and this is the one I've just loaded. And if you're interested at all, you can see that Archer 2 has a whole bunch of other software installed as well. Not this. Excuse me, I'm getting my module commands wrong. And it has a whole bunch of compilers and software packages and tools and all sorts of things already installed. So that's the module avail command, which will tell you that. So it would be nice to know if people have managed to log into Archer and have managed to load the Python module, and then you can type Python, and you get this script up here. Okay, so there's a couple of questions here. It's good to see some people are in. Now I should say, if you're not managing to access Archer today, That isn't necessarily a huge problem because you can run Python locally as long as you've installed Numpy locally. Let me just have a look for. So just looking at the documentation for logging in. If anybody needs the documentation to how you log into Archer, there's quite a nice quick start guide, which I've pasted into the chat. Good question, Gavin. Does the Cray Python include pandas? I've no idea, but we can try it out. Looks like it. Looks like it's there as well. The Cray Python is a sort of optimized Python install on the Cray systems, but it comes with a bunch of packages already installed for you, such as SciPy and NumPy, and I've looked at Pandas, and some of the machine learning packages as well. Yeah, as I say, okay, what we need to do this lecture, or at least to do this lecture efficiently or sensibly, is a Python interpreter here, like I have here, with NumPy installed somewhere. Now, if you don't have those things, and you can listen to the material, and you can read the material, you just can't try it out yourselves. You can't try it out in practice, which is useful, I think, for learning this kind of stuff, trying it a bit hands-on. You can always come back at a later date and try it out once you get access to Archer 2 or once you've installed NumPy on your local system. If anybody is having real problems and haven't got NumPy locally installed or don't have access to Archer 2, please do let us know in the chat so we can help with that. What I'm going to do now is assume that the majority of people are up and running with some kind of Python setup which they can use, and then we'll start going through the NumPy material. I will try and keep an eye on the chat as we go in, but I may miss any questions for a minute or two, so I'll get back to you if I do miss them, or if you want to unmute and shout at me and tell me to stop, that's perfectly fine as well. And as I say, if there are any other questions as we're going on, please do just chip in. Okay, so NumPy, or numeric Python, is an add-on to Python, a library for Python, which supports multi-dimensional arrays and something called ND arrays, and matrices and linear algebra operations, and a bunch of other kind of functionality, which is key to scientific simulation and useful for applications. So random number generation, Fourier transforms, polynomial operations, those kind of things. So it's a library that's designed to give large-scale matrices operations for Python. But crucially, it's also designed to be fast. So at some level, it probably compiles down to a C library, which calls fast libraries such as MKL or Cray-libsci, which means so all that is a fancy way of saying it's been optimized to give you good performance. Because Python primary goal is not necessarily to give the best performance. It has, it's designed to give other things such as easy programming and nice integration with GUIs and all these kind of things. But if you want to use Python for computationally heavy things, then it's definitely useful to have a library which supports multi-dimensional arrays, but also a library which is efficiently implemented, so it maps down to a fastest functionality it can. That means that installing NumPy can sometimes be slightly tricky, or making sure that you get NumPy installed efficiently slightly tricky, because ideally you need it to compile so that it uses some built-in maths libraries and some of these kind of things. But the nice thing on this Archer system is it's all installed for you in this Cray Python package, and that links down to the fast math libraries and things like that you need. Okay, so how do we use it? Well, just like any other Python library package, we want to import it, import NumPy, And we can give it a name, so we can import NumPy as NP, which is a pretty common way of doing it. So import NumPy as NP just means we don't have to type NumPy all the time. We can do NP instead. And that's imported fine, so we're happy enough with that. And so from there we can create NumPy arrays. Okay, and the NumPy array is created. Let me get my mouse back as follows. So the examples here are in the notebook web page that you can go through, but a equals np.array, open brackets, and then I can define data. So here I'm creating an array, a one-dimensional array with 3 elements. First element is -1, second element is 0, third element is 1. I can also create a NumPy array from another NumPy array. We can see here, then I can print out those arrays. If I could spell properly. Those arrays, and you can see we've got this 3-element array, -1, 0, 1. If I print out B, then we have exactly the same thing, -1, 0, 1. And we can confirm this is actually not a sort of a built-in list or something like that in Python. It's actually an array type, because if we do type of the variable, it will tell us what it is. And it says it's class numpy.nd array. Okay. So it's a great question that's just come in. It would be the first thing I would ask as well. Because we've created B from A, the question is B at some level just a copy of A, but if I change A, B changes, or is B a separate thing? And the answer here is that B is created from A, but it's its own copy. It's a standalone copy. So if I make a change to A, then it won't make a change to B. And we can see that by skipping ahead slightly in the material and doing this. So if I print them both out, I rushed through that, apologies, but all I've done here is I printed out both arrays. I printed out A, and it gave me -1, 0, 1. I printed out B, and it gave me -1, 0, 1. So they both have exactly the same data in to start with, because I created B from A, so it should. And then here I've updated the first element of A, and instead of being -1, I've set it to be 1. And now when I print out A, I can see it's now 1, 0, 1. If I print out B, it's still -1, 0, 1, because I haven't updated B. So even though I created B from A, it is its own data structure with its own data in it, and they're completely. Does that answer your question, Vladimir? Cool. Yes, so as the web page says, the NumPy arrays provide you multi-dimensional arrays with elements of the same type in multiple dimensions. The arrays are very much like Fortran or C++ arrays, which should be efficient both in terms of storage and in terms of execution runtime of your applications. If you were just to do this kind of stuff in Python without NumPy, generally you'd be using lists of data functionality, but because the way lists are implemented, there's all sorts of object-oriented overheads associated with those lists of methods and classes and pointers and these kind of things that were implemented. So that's why the NumPy arrays exist. So we can also create NumPy arrays in different ways. So we can use this sort of arange function. So we could now say, let me get my my screen back. Again, I can't spell. Excuse me. So we've used this range function here, np.arange, which creates a range of values when I initialize my array. So actually I'm saying here, create a range of values from -2 up to 6, up to but not including 6, in steps of 2. So that is is created a 4-element array, -2, 0, 2, 4. It doesn't go all the way up to 6. If I'd have said create the same array up to 7, then you should see we should get a 5-element array, -2, 0, 2, 4, and 6. And this is very similar to the range function for standard lists in Python. So that's a way of creating and initializing a NumPy array with various sets of numbers. We can also create a linear space as well. So there's a similar way of doing it. We type it in. Very effectively, we're creating a range, but of course, we're now not limited to integers here. We can create step point and intervals, so we can create a range within a floating point set of numbers. So here we're setting the range of -10 and 10, and in this case it is inclusive, and then we're saying how many points we want inside that range. Now there's a couple more functions within the web page where it asks you to guess what they do. So here is an example, which is b equals np dot zeros. Let's do a c equals np dot ones. Now, now we can hopefully easily infer from the names what's going on here, but these are the two of the methods that NumPy provides you to create an array and initialize it when you're creating it as well. So b equals np.03 should create me a 3-element array with each element 0, and likewise np.ones equals 10 should create me a 10-element array with each of the elements 1. And let's just print that out. Check that is correct. Sorry, not A. Print out B, and then print out C. So NumPy gives you a set of functionality to provide create arrays and initialize arrays as well in various different forms. So I see there's a couple of questions within the chat here. So how do we create a pointer from A? It depends what you mean by create a pointer, Ben. It depends what functionality you need there for creating a pointer in Python. If you're trying to slice or get access to the different parts of the arrays, you wouldn't do it with a pointer. There's a bunch of functionality which we'll come across, which we'll do that. I guess the question is, why do you want something that looks like a pointer to get access to the array in Python? And then are the values in the array always floats? The answer is no. You can create arrays with different NumPy arrays with different values with different data types. So we should come across an example of that in a little bit. Okay, if there's no other questions. So then we can, once we've got an array, then we can query the array for a range of things. Because Python is an object-oriented language, there's a bunch of functions which are attached to the arrays, or a bunch of methods which are attached to arrays, where we can look at the number of dimensions, the shape, the size, and the data type. Going back to your previous question, Vladimir, the data type of the array itself. So I've got my array here, C, my C array, which is elements all set to 1. Then I can print out dimension of C, so this is a one-dimensional array. I can print out the shape, it's 10, got one dimension of size 10. I can print out the size, that's of size 10 as well, and I can print out the data type. Here it's telling me it's a 64-bit floating point number that's being used there. It's possible, of course, to change the type of an array, as I mentioned. So you don't have to use a default type as being used here. So if I wanted to create my linear space or my zeros or ones array, I can change the data type used. So an example would be like this. Here we've specified the array and we've specified that we want it to be integers, or you could do 32-bit floating point numbers, or you could do 64-bit floating point numbers. And so NumPy has a range of different data types which we could use: integer, Boolean, unsigned integer, float, complex float, times, dates, these kind of things. There's a bunch of data types we can use there. And you can specify, actually, I could have specified, I think, although it's not something I've done for a while, I think I could have specified this as I. So you can use I as integer as well. And so if you have a look online, there's a list of all the NumPy data types and then their single character reference, which you can use as here. Now, it's also possible to map between different array types as well. So you could take an array of integers and create a new array of them as Booleans, as true or false values as well. Those kind of things are possible. Now, of course, the things that we've just looked up here, number of dimensions, shape, and size, only really start become interesting once we go into multi-dimensional arrays. And so far, we've only looked at single-dimensional arrays. So we will go on and have a look at multi-dimensional arrays. I should also say that this way of creating ones and zeros. So before I had b equals np dot zeros 3. But I could also do I should be able to do an np here, well, and specify when I create arrays with zeros or ones, the data type we use there as well. And there are a bunch of other things you can specify at this level of creation, which we'll come on to. So that's single dimensional arrays, and we've sort of started to see a little bit the kind of things we're going on. Vladimir, it's a good question. Can you change the data type of an existing array? I think yes, you will. Yes, you definitely can, because there's an as type function, so you can say array equals array.as type, and that would go through and change it. How it does it actually under the hood, how it does it actually under the hood, in terms of does it copy it to a different array and copy it back as a new data type, or does it just go through each element individual? I don't know. But yeah, definitely there's a function where you could say, let me see if I can do this without it looking stupid. I'll get this wrong somewhere. So here we can see I've taken my B data type, which was integers, and said copy it to array A as floats instead. And actually, if I'd have done this, B equals B as type B, then that would have changed my data type in place. So we can do that. We can change data types as well. The good question here as to whether A equals B is the same, sorry, B equals A is the same as B equals NP dot array A. Can I use B equals A instead of B equals NP dot array A? Well, if I do B equals A like that and then print them out, then change one element of A, can see in this context, we have what we could have seen, what sort of what Ben I think would call a pointer. Whereas if I do B equals A, I actually my array B is actually just a copy, a direct link to the array A. So if I change it in one place, I change it in both places. So there is definitely a difference between saying B equals A and B equals numpy dot array A. Because in the case where you say B equals A, you effectively get a just another name for array A, whereas in B equals numpy array, I get a new data structure initialized with the values were in A. Is that answer your questions? Okay, so we've done single dimensional arrays, and we've done how you play around with the arrays a little bit. What do multi-dimensional arrays look like? Well, as an example in the web page, so we can say mat. That's what you want. The idea is it's a matrix, more than a one-dimensional array, equals numpy array. You can see here we're now using nested brackets in the sense that each of my dimensions is defined by a set of square brackets. And then there's a set of square brackets which contain the whole dimensions. And then again, if I print this out, now see I've got a two-dimensional array. Each dimension has 3 elements. The first dimension has 1, 2, 3 in it, and the second dimension 4, 5, 6. And we can see that now, if I ask what are the number of dimensions of this object, I've now got 2 dimensions. It's got a shape 2 dimensions, each with 3 elements, and an overall size of 6. Okay, so we can see that these functions become more sensible, more useful at this stage. And then I can this is creating a numpy array out of a set of lists. And now there's a couple of commands for you to go through yourselves and have a look at here. So the question is, for a number of these operations, what is going to be the shape of the arrays that are created? This is the first one. I've just copied and pasted in here from the web page. This is the first one in the example, and then the second one is for J. I'm going to copy and paste that one in as well. I've not quite copied and pasted it correctly. And so the question is, can you work out what shape I and J are before you run the command I.shape and J.shape and print that out? So just have a quick look at that and see if you want to see if you can work it out, and then I'll talk you through the things there. And if you have any other questions, feel free to ask them just now. And Vladimir, I just saw your question. Yeah, it's a good question. How do you create an array from arrays? Yep, you have to put the square brackets around it. Otherwise, it thinks it's going to be those A's are sort of input the different parameters in the Numpy array function. So exactly if you put there np.array open brackets square brackets a will do the job. Any other questions before we get going? Okay, so we've got two arrays here, I and J. They're both multi-dimensional arrays. The question is, what we're going to see the shape of I and the shape of J, given that they've defined them in these ways here. So hopefully we should see that we've created I as a two-dimensional array because we've got two sets of these brackets going on here. So let's have a look at what the shape of I is. A two-dimensional array. In the first dimension, there are 4 entries. I've got 4 lots of these, and then each one of these is size 3. So the shape is going to be 4 by 3, and the size would then, of course, be 12. So and then for J, we've got a slightly more complicated example because actually we can see we've got 3 sets of brackets going on here. And we've got a set of self-contained dimensions here where this would be a two-dimensional array by itself, a 4 by 2 two-dimensional array, and this would be a 4 by 2 two-dimensional array, and this would be a 4 by 2 two-dimensional array here. So if we print the shape of J, you see we've got a 3-dimensional array with 3 lots of 4 by 2 matrices in it. And then, of course, the size of this is going to be 2 times 4 by times 3. So you can have multi-dimensional arrays here. Now, off the top of my head, I cannot remember what's the maximum number of array dimensions you can have for NumPy. I'll look it up later. But this is how you create multi-dimensional arrays. Now, the other thing I've not shown you here, but it's probably useful, is you don't have to create arrays initialized or with a defined set of inputs, or arrays that are initialized with 1s and 0s as we had before. We can also create empty arrays. So I could do an array like this. And that creates me a single dimensional array of 10 elements. But it's not initialize them, so it's not set them to 0 or 1, and they could have random values in there. Actually, if you have a look, turns out we've all got 1 in them in this instance. But if I created a, let's see if we can find one that doesn't count me ones. There we go. So it turns out we had hit some memory there, which the values 1 had already been initialized into. So it was getting that. If I created my array F here, 109 elements, it's empty, and you can see there's all sorts of numbers going on in here because I've not initialized it to anything. So some of them are very small, some of them are 0. There's not actually any that are very big here, but we can see that if you don't need to initialize an array, you can also create an empty array and then iterate over it and do things with it. And that may save you, it doesn't matter if you're creating small arrays, it's not going to have a big performance a difference either way, whether you initialize them or not. But for a very large array, of course, initializing it may be expensive to do, so you don't have to set it to 0 or set it to 1 if you're going to create your own values to put in there. Okay, so that's creating the arrays. You can as well, I think, that's a good question. Can you convert normal Python lists to Numpy arrays? Well, yes, you can. Yeah, so if you just pass it the Python list in as the first entry, just like when we put in these square brackets in, then that should do exactly that. So C equals Numpy array is actually taking a Python list 1, 2, 3 and pass it in to create the Numpy array. So that should also work for objects outside that. So if I said, again, I'm going off script here, so my Python will all go wrong, but if I said A, so exactly that. So what I've done here is my A array is actually a Python list. It's not an array, it's a Python list. And then I've created a NumPy array off the back of it, and it produces a sensible NumPy array for me. And we could look at the type of it as well. Let me just remember my syntax here. And we can look at the type of those two things as well and see what they look like. We can see that A is a list and C is a NumPy array, a NumPy ND array, n-dimensional array. Any other questions? Okay, so and you can actually, so there's an example as well here, which I'm just going to copy straight out of the notes. So you can also create complex number arrays in NumPy as well. Here I've taken a Python list, 2-dimensional list. 1, 2, 3 is the first element and 4, 5, 6 the second. I want to create a matrix from it with NumPy array, and I'm passing in the complex. I want it to be a complex number array. And then if I print out matrix, we can see that it's taken these numbers here to be the real values, and the complex values are all set to 0. Now, I'm not an expert on the complex number stuff in NumPy, so if you're going to ask me how do I initialize the complex number parts of these, I would have to go and look it up. But the complex number functionality is there if that's something that's of use to you or your application. Okay, so we've created arrays. We spent a lot of time creating arrays. Actually, you want to use your arrays. So how do you do that? Well, in NumPy uses a square bracket notation. So if I go back and create myself a new array, create myself an array from a range of 8. So it should have created me an array with 8 elements, 0 to 7. And it's done that, and that's a Numpy array. I can then access individual elements of those by using the square brackets. To print me the second element of A, the Python is like C in that it indexes its array elements from 0. So that's array element 0, array element 1, array element 2, array element 3. So I said print out the second element, element 1. That prints out this value here. Okay, and I can also print out ranges. And so I can say print A from the first 4 element of A to the 4th element, but exclusive, so don't include the 4th element. It'll print out 0, 1, 2, and 3. And I can also get it to print out sort of ranges. So what's the top and bottom end of those elements? Now this is a little bit of a rubbish example because my entries in the array are the same value as the indexes. But if I created a created an array where I start at 8 and go to 9, 10, 11. So again, if I print out A1, that should give me the element 9 here. If I print out 0 to 4, it should give me 8, 9, 10, and 11. If I said print out A element 0 and the element and the 4th element, it should give me 8 and 12. So ranges are exclusive. They don't include the last number you put there. But if you ask for specific elements like I'm doing here, ask me for the 0th element of the array and the 5th element of the array here, then it will produce those exact values. And then you can also do sub-sampling in there as well. So I specify go from the 0th element to the 8th element of the array, and do it in chunks of 2. So that's what this 2 means here. So take the first element, skip over, take the second element, skip over, take the first, third, 5th, and 7th, or because Python indexes from 0, 0, the second, 4th, and 6th elements of that array, and that will let me subsample the array as we're going down and using it. It's also possible to do reverse ranges in NumPy, so you can use negative numbers to go from the end of the array rather than the beginning of the array. Okay, so A minus 1 says give me the last element of the array, and likewise if I said print A minus 2, it gives me the second last element of the array, and print A minus 3, it gives me the third last element of the array. So you can see we went from here to here to here, and you can do ranges back in time as well. So we can do something like back in space. I shouldn't have said time, back in space. It says go from the second element to the, so your range is from the second element, so actually the third element of the array. So array position 2, but that's 0, 1, 2, 0, 0, 1, 2. Then go to the third from the end, which we saw before was 13. So go from 10 to 13 in chunks of 2. 10, 13 in chunks of 2. So it gets element 10, data entry 10 here and data entry 12 here, and prints those out. So you can access this, and this is exactly the same if you had a multi-dimensional array. So you can use either lots of square brackets, one set of square brackets for each dimension, or we can use what we call a tuple, which is square brackets with commas in between them, and we'll see that in the next example. Any questions about accessing array elements? Okay, well, let's move on. So again, so as I said, that's for what we've done through here is single dimension array accesses. We can also do the same thing for multi-dimension array accesses. So for laziness, I'm just going to copy this directly from the web page. And then we can have a look at how you access individual parts of the array. So you can see we've got a 3-dimensional array with 2 by 2 by 2. It's 3D cube 2 by 2 by 2. And we can access individual elements either by using different square brackets, print 1, 0, 1. So that says take the first dimension, 1 in the first dimension, 0 in the second dimension, 1 in the third dimension. So it says you want to take 1 in the first dimension, so it chooses this one, this bunch over here, and then 0 in the second dimension, so it chooses this part of that set of dimensions. So that's not the 0, the first in the first dimension in the leading dimension, and then the first element, the first set of dimensions there, and then it takes element 1 there. So that's the second thing in the array, and it picks that out. Okay, so that's how I can move around my multi-dimensional array. But I could also have done the same. So using a different notation format that NumPy supports, which would be it does exactly the same thing. You can use the square brackets, or you can use commas inside a single square bracket, and it'll do exactly the same thing. And then, of course, we can also print out ranges of dimensions. Print me all of the second entry in the first dimension. So that prints you all of this chunk over here. Or I could say just print me all of the this part of a dimension. So I don't have to select the whole shebang, as it were. We can also look at what happens if we try and go beyond what we have available in our array, in our matrix. So I can say, give me the third entry in the first dimension, and actually we know the shape is only 2, 2, 2, so there's nothing in there. And it will tell me, okay, index 2 is out of bounds for access 0 with size 2. So what it's saying is I've put the number 2 in here, but that access has only got a size of 2, so you can only take numbers 0 and 1. And beyond that, it's going to have a problem, okay, because that data doesn't actually exist. So you've asked for something outside of the data space that we're using here. Okay. Fine. Okay, so the next part of the practicals, unless there's no questions about that, talks about something we've already covered, which is this idea of data, so creating copies of arrays, whether we create a reference or a shallow copy of an array. So just to run through this again, when I create an array, what's happened here, I did my array creation here, so create me a Numpy array and call it A. And then I said B equals A, and that takes a reference to that A. So B I can use to access it, A. If I make any changes to A or B, they both see the same changes. So effectively, they're both referencing the same data sets. Whereas if I had done what I did before at the beginning, where I said that would be a copy of the array. B would be a copy of the array, and I would be able to change both of them independently, and they wouldn't impact on each other. We can have a look at the identity. So one way of checking what's going on is you can have a look at the identity. So let me revert to the example I had before. B equals A. You can use this ID function, which effectively is going to print out some kind of pointer, a memory reference, and I can see now that A and B both have the same identity. If I did B equals Numpy array A, and then did identity of A and identity of B, you can see they've got different numbers going on here. So they're actually different objects. You don't have to use this np.array equals B. There's actually a copy function which lets us copy arrays and create copies of them. So if I did C equals A.copy, this effectively does what is very similar to doing np array equals. And so C equals A.copy will take all the data in A and create a new array from it, which you can use, where you can see it's created from what A was set to 26.2, but I can change A and it doesn't change C. Okay, so this is maybe an easier way to create one NumPy array from another. This copy function, because you don't have to, if you said np array equals A, you may have to pass in a bunch of other parameters to say what kind of data type do you want and other things here. Whereas this copy will copy all that metadata for you as well. Okay, so now I've not quite finished the NumPy stuff yet, but we had a break scheduled now for 15 minutes. So what we'll do is we'll come back to this NumPy stuff at 2:30, just after 2:30, and then we'll go on a little bit more for the NumPy stuff, and then when we're finished that, we can have a look at the MPI for Path. And if you've got any problems accessing Archer in between time, then during this break, we can help you get logged onto Archer, hopefully. So drop a message into the chat and we'll contact you separately to sort that out. And if there's any questions about the material we've covered so far, let me know. Okay, so we should crack on then. So we've seen you can access individual elements of the array and individual dimensions of the array. You can also slice and view the array. So we can create a view of the array. So you can create a slice or a view of the data. For instance, if you only wanted to collect, or work on a subset of the dimensions or a subset of the element from each dimension, you can create what's called a slice or a view of that data. And the nice thing about it is it doesn't need to copy the data. It doesn't create a new array or use more memory or anything like that. It just creates a set of views which your Python can use to iterate over that. So what does that look like? Again, it's using the square brackets notation and the square brackets notation and colons to specify ranges. But let me set up the example that's in the on the web page on the IPython notebook for this, which is an array called A. We should really move away from calling arrays A and B and things, shouldn't we? Have more descriptive names. We've got an array A, which is two-dimensional. We should hopefully be able to see it's a 3 by 3 array. By 3 array. But if I wanted to take a slice of that array, so let me print A out first. I can then create a new view onto that array, which I've called my slice here, which looks like an array itself. So Python thinks it's a Numpy array. And then that can give me a subsection of the array which I may want to work on to do other things. You can see that I have taken what I want to take is the second to the third elements of the first dimension and the first to the third elements of the second dimension. And that will say, okay, 2 to 3 on the first dimension is that's 0, that's 1. So this is the first entry of dimension 0. This is the second entry of dimension 0. And this is the third entry of dimension 0. So that's selecting that. And then this here says I want to take elements 1 up to 3 inclusive. So this is element 0, this is element 1, and this is element 2. So that picks me out a 1D array of size 2 with elements with data values 8 and 9 in it. So it's slightly confusing here because of these range numbers here. But effectively what I'm saying is I want to take a slice of the array from 2 to 3 and from 1 to 3. And that equates, well, from 2 to 3 in the first dimension is that's 0, that's 1, that's 2. So 2 up to the size, so 2 to 3 is, say, select this bit here. And then from 1 to 3 in the second dimension, well, this is now the second dimension, 1 to 3, that's 0, that's 1, and that's 2, and overall there's 3, so 1 to 3 is those 2 elements there. Now, of course, if I'd have done I've just done something like that, it would only give me a single element. So it's going to say second dimension, the second 0, 1, 2. So 0, 1, 2. That's what that 2 means. And then that 1 here means 0, 1. That should print out. My entry should be 8. And if I'd have only asked for 2 there and then 1 to 3 here, it does the same thing as I had before. Okay, so it gets me to these 2 values here. Slightly differently, there's a slight difference in what I've done here because you can see actually this thing here is it's got 2 dimensions. Now one of them happens to be 0, but it's got 2 dimensions. And this thing here has only got 1 dimension. So we could see the difference between those. This is again the challenge of going off script. I forget what I'm meant to be typing. We can see my new slice has got one dimension. It's returned me an array with one dimension, whereas my slice should have returned me an array with 2 dimensions. Okay, so this is slightly confusing. Well, it is to me anyway, slightly confusing in what's going on here. But really what we're saying is you can create views onto your data. So my overall data is this array called A, which is a 3 by 3 matrix. I can create a view onto that, and here I've called it my slice, by specifying a range of those dimensions we want. So it says first, it gives me one element in the first dimension and 2 elements in the second dimension. If I specify it with these ranges, it'll give me a view which is 2-dimensional. So the original array was 2-dimensional, the new array is 2-dimensional. It doesn't matter if there's only 2 elements from 1 dimension in it, it gives me a 2-dimensional array. I can also do the same here and collect a range of values here in the second dimension, but 1 entry in the first dimension. It'll give me a 1-dimensional array back. And so this will generalize into n-dimensional arrays as well. So I could create 3 or 4-dimensional or 5-dimensional views into this data structure here as well. So I can see different parts of it. And so that can be useful when operating on different parts of array. And we can see we don't have to just use that slice for viewing the data. We can also use it for updating the data. So I could say I can specify my slice, all the elements in my slice, but set them to be 10. You can see that now these two are 10, but we should also have changed the original array, which was defined like this. So these 2, 8, and 9 numbers should now be specified as 10 instead. We can see we have updated that, so we can use these views or slices to take chunks of the data and work on them separately. Okay, so there's a little challenge for you now in the course notes or in the web page to take this array, and I'll copy and paste it just like you can. The M array. What we want you to do is change all the elements with values 7, 8, and 10, 11 to be 1,000. So we want to change this sort of bottom square of a matrix to 1,000. So can you create a view which lets you do that by saying, creating something like my equals and then what you need to do is decide what numbers are either side of these colons here, and then once you've created my m, you can say my m equals my m colon equals 1,000 like I did here, and that will update your data. So give that a shot and come back and we'll see how it goes. If you have any questions, drop them into the chat. Okay, hopefully you've had a little chance to play around with that. So I did my own version of it, again, with all the potential to embarrass myself, but my own version of it whilst you're hopefully doing it yourselves, and just so we could run through it here. So we had this M array, and we can print out M, and what we wanted to do was specify that 7, 8, 10, and 11 were all updated to 1,000 in the bottom using one of these slices or views. So I could create a my M view where I say in M take the second and third entries in dimension 0 and the first to 3 entries in dimension 1. And because again we're indexing from 0, I don't know if you remember, slightly annoying syntax, we're indexing from 0. So that's the 0th entry, this is the first entry, this is the second entry, so 2, and the third entry, 3, So that is these two things here. It says select this and select that. And then inside those, it says select the first and second entries. So we know each one of these is 3 elements long. So that's 0, 1, 2, 0, 1, 2. But we know we're only taking these 2 bits here. So it says take 1, 2, 1, 2. And so effectively with this slice, we've just taken those 2 elements and those 2 elements there. And now I want to set them to be 1,000. If I just do this, my equal to 1,000, because of the way Python works, what it doesn't do is go through and update all those elements of the array. Actually, it overwrites my m with a new variable, which is just an integer of 1,000. So that's the wrong thing to do. The reason that we have to use this square brackets colon is to say, actually, here I don't want to create a new object with the same name, which is an integer. I want to access the elements in this array by view, and colon comma colon for a 2-dimensional array means all the elements, and set them to be 1,000. Okay, and now I can see if I print out my the view, I've got 1,000, 1,000, 1,000, 1,000. So that's worked. If I look at the overall array, I can see all the elements are what they were before when I had them here, except the bottom corner, which is 1,000 by 1,000 by 1,000 by 1,000. That's how the kind of how the slices and views work. So it's a great question, Ben. Why would you want to not change the values directly without slicing? In this example, you could absolutely do that. So there's no reason why you wouldn't necessarily want to do that. The slicing and the views becomes useful when you want to start passing this kind of stuff to other functions. So you want to pass it to a function, which may pass it to another function, and pass it around. And so it can be useful just to create a name for that slice, which you can then use elsewhere. So it's purely a convenience thing, but a useful convenience thing. You don't necessarily have to create a my. You can use the slice directly, as you pointed out, but in some scenarios where you want to pass it through functions, then it's useful to have a name for that to pass it in. Any other questions? Just as we can slice, we can also reshape matrices. Matrices. So we can go from 1-dimensional to 2-dimensional to 3-dimensional, as long as the size of the array doesn't change. If we have a look, if we take an example here, and I'll create an array. Let me get my cursor back. I've got a 6x6 element array. Sorry, I've got a 6-element array, single dimension 6-element array called my array. I can also then reshape that. So if I print out my array, I can use this shape function here, myArray.shape. So shape is a function of that object, the Numpy array object, and I can pass it in a tuple which tells it the shape I want it to have. So here I had a 1-dimensional array of 6 elements. I've now changed it into a 2-dimensional array, 3 by 2. And you can see when I print out my array, it's now changed this into a multi-dimensional array down the size here. So this will change your array as long as the size remains the same. Okay, so I can change it back again. and we've gone back to a one-dimensional array of 6 elements. I could actually also do this. I can create a 2-dimensional array, but the first element only has 1 entry, so I can also keep that. So if I wanted to then reshape that into 3 by 2, it works perfectly fine. So those things all work. I can change my data layout by just using this shape function and passing in the layout I want to. Now, of course, if I change this to I change it back to a 1 by 6, a 1D array of 6 elements, and I want to change it to something else, 8 by 4, it's going to complain because my array size is wrong. 8 by 4, 8 times 4 is not equal to 6, so it's going to complain there. It's possible for me, if I want to resize an array using a different function. So you can see here that I've actually changed the size and shape of my array by taking my original array and making it bigger. But this resize array will let you take arrays and make them bigger and change their shape as well. But it does so, it may increase padding or copying of the data when it does it here. So you can see what it's actually done is it's copied my data in enough times to fill up the array. So I've got 0, 1, 2, 3, 4, 5, and then 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, etc., all the way up to here. So that may be not what I want to do, but it is possible to take an array and resize it to give it different configurations. Yeah, is there any questions about that? Okay, so then there's a bunch of things you can then do with so you know, Numpy strength is these arrays, but of course it gives you a lot of additional functionality on top of that, which is why it's useful. So there's a bunch of functions: concatenate, split, flatten, ravel, stack, tile, repeat, trim zeros, fill, mesh grid, all these kind of things, which let you do different things with these arrays as well. So you can take multiple arrays and stick them together with concatenate. You can split arrays, create new arrays. You can flatten a multi-dimensional array down into a single-dimensional array. You can ravel. Which flattens your array, but in a slightly different way. So it makes sure that the data is contiguous in memory, and so that may be useful for you as well. You can tile and repeat and these kind of things. So we're not going to go through these in detail here. That's sort of something for you to have a look at in your own time, but you can have a look at the list of different ways you can sort of split and flatten and reshape arrays in Numpy, because there's a lot of functionality there. And if there's things you're trying to do, there's probably a function that's already available to do that kind of thing for you. And there's also something sort of more advanced or fancy, it's quite often called indexing, that you can do to go across the data in your arrays. So you can actually create a set of rows and columns to pick out individual bits of data in your array. So we'll go through this example we have here. The lecture notes, the lecture webpage. We created an array. It's a 4 by 3 array. And then we can create a set of row and column entries for those. We can specify where we want individual elements to come from here. So effectively what we've specified here is two lists which identify data points in those particular positions. So effectively the first thing is element 0, 0. So 0 in the first direction and 0 in the second dimension. So that's this element here. And then we want to say 0, 2. So 0 in the first dimension, that's here. And 2 in the second dimension, that's this element here. And we've picked out that element there. So 0, 2, 0, 2. And then we want to say 3 in the first dimension, that's this one here. Pick out 0 and 2 from there. So pick out 0 and pick out 2 from there. So we can pass in these matching sets of rows and columns which we want to pull out, and this will pull out individual elements, a 4-element array, but those individual elements in here as well. And then that queue that way of producing these views is so that this way of looking at the data using these rows and columns, and we don't have to call this row and column, but that's effectively what they are, rows and columns. We can see is actually produced as a copy of that data. It's not a view or a slice, it's actually a copy of that data. So we can update Q, which I created from these rows and columns. It initially had the data that was in P, but now I've updated it and it's got the data, its own data in it here, and that has not affected the underlying arrays or matrices that I was using there. You can also use masks, Boolean masks or logical operations to work on our data, and this can be very useful for sort of processing data sets. So we can say, we can either take a whole set of arrays and convert them into a new set of Boolean arrays. We can also use a logical condition and say, please go and find me all the elements in this array, which is of a certain value. So here's an example of a new array. We have this two-dimensional array. I want to find all the negative numbers in this. I want to find all the entries which are negative numbers. So go through and find all the elements which are of a certain value. So here, print, take the matrix M and find me any element of a matrix M where it's less than 0, and it's return me a one-dimensional array of all the negative, non-positive, non-zero numbers in it. So I can go through and cut up my data that way. And again, this is going to be a copy, not a view. So I get a new version of that data, which lets me play around without updating the original data. And I can do a similar kind of by converting data to Boolean values, for instance. So I could say what I've done here is created two separate arrays, one called A, which has got the values 1 to 9, 0 to 9 in, and one called mask, which has the values true in, and it's the same size as A. And then I can set individual bits of this one here to be false. You can see now I've got elements in this mask array which are either false or true. And then I can use this mask array to select bits of the data I want. So I can say what I've used this Boolean array of true or false values as an index into my main array, my A array here. So I've said, actually, if I pass this in here, everywhere where I've got a true, I'll get a value back. And everywhere where I've got a false, I won't get a value back. So if you could, for instance, process some data and you want to mask out some results, you only want to get the elements which are, associated with a man or a woman or something like that, or a different species, you can create a Boolean map based on that and then pass that in as an index selector to say me only the results which correspond to that functionality. Okay, so beyond purely setting up, moving around, copy and reshaping data, it's also possible to give you what we call element-wise operations on data. So if I take two arrays, I can actually update them without having to do a loop over the elements of the array. So here's some examples from the notes. I've created two arrays, both the same, two-dimensional arrays, both with the same numbers in them. I can now try doing some operations on them. So I can take the array and I can multiply every element of that array by minus 0.1 and I'll get a result. Now that hasn't actually updated A because I never assigned it. It's still the same, but I can do element-wise operations by just running a mathematical operation on the array itself. And because it's a Numpy array, we'll do these kind of operations. This is element by element operation, so it's not a matrix multiplication, it's a single element going through and timesing all these things together. Of course, that makes a difference because there's a difference between matrix multiplication and dot products of matrices. So if I did A times B, this is not the same, so my array A is this one here, and my array B is the same as that one here. And we can see that what it's gone through and done is it's taken individual element 0 of A and B and times them together, and then 1 and 1 becomes 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. So you can see that NumPy matrix A times NumPy matrix B is really just element by element matrix multiplication, so element by element multiplication. If you wanted proper matrix multiplication or matrix vector multiplication, then you need to use a different function here. So instead of just doing A times B, you need to do wanted to actually do the matrix product, then what you would need to do is A dot B transpose. You need to transpose the B so it's the same shape as the A when it's doing the matrix multiplication. And this dot T here does the transpose function. So let me just show you. If I go you can see that B is a two-dimensional array 0, 1, 2, 3, 4, and then 5, 6, 7, 8, 9. But if I transpose it using this function b.t, that produces me a new matrix, which is instead of being a 2 by 5 matrix, it's a 5 by 2 matrix with the transpose has been undertaken. But that hasn't actually changed b. If I wanted to actually change b, I'd have to go. I can actually store the results back. But that's how you can do multiplication or operations on these arrays. And so, of course, it depends on the data types of your arrays. So if I had mask, if I had character arrays or things like that, which are possible in NumPy, it wouldn't necessarily do something sensible, or it may not do anything at all. When I try to do a times b, it may give me an error. Any questions about that? NumPy also has a bunch of other functions built in there. So one of them would be random number generation. So you can see I can use this numpy.random.ranf function, so random float, to create a new array of 10 elements which are randomized. And this will give me each element in that array will be a random number between 0 and 1 inclusively. You could also potentially do you can see that the random f function, randf, produces you an array of size 10, where unfortunately the randint function here produces you an array. It doesn't produce you an array, it produces a single value, and 10 here now specifies the range of a random number. So you can see if I put 10 here, it'll give me a random number between 0 and 10. If I put a 1 there, it'll give me a random number between 0 and 1. So if you actually wanted random integer array rather than a random floating point array, then you can specify that as a different function. So you can say here I can say starting at 0 with the highest number being 10 and 25 elements, give me a random an array of random integers. And as the example is in there. Now we know if we didn't want a single dimensional array here, we wanted a multi-dimensional array here, then we could reshape that or size that. We could say we can reshape it into whatever we want. And in fact, you can combine that reshaping with the creation of a function of array. So we could do this: a equals np.random.randint, starting at 0 with a height of 10, size of 25, and then we'd have a 5 by 5 array initialized with random numbers, integer numbers between 0 and 10. And so, I mean, we have to be careful using random numbers anyway. So you need to understand how random the random numbers are. So I am no expert on the Numpy random number generators and how statistically random they are for large sample sizes and these kind of things. It's worth doing some background reading if you're going to rely on these for in-depth scientific results. Or at least it decided to tell me it stopped working. So yes, you can also do selecting random numbers from a distribution. So the example here in the notes is select from a normal distribution, a standard normal distribution. Let me just put this into the Python window. There's some examples in the notes here to say, there are other ways of generating random numbers. Have a look at the Python NumPy documentation. Have a look around there. Because we're slightly behind schedule here, but we won't stop to do that just at the moment. But I just want to get on to the file operations and performance, and then we can take a little bit of time to have a look at one of the examples and then briefly talk about the MPI for Pi stuff. But of course, if you have any questions, do let me know. So NumPy also gives you a set of functionality to do file operations with data, reading data or writing data. And so they can be very useful. So here's an example. We have in the online webpage where we've got two sets of arrays. One is X and one is Y. So this, I could be using this to create a graph where I've got entries for my X-axis and entries for my Y-axis. And these are just been from a range and a random sampling of data. And then I can use this stack function here to put those two things together. So this is one of those extra functions we talked about where you can take multiple data sets and bring them together, like the Ravel one and things like that. So I can stack these together. So I've got now a multi-dimensional data set where I've put individual entries together. So I can say my 0 has been paired with my first entry, and this has been paired with my second entry, and this has been paired with my third entry. This has been paired with my fourth entry, etc., etc. And then I could save this data out to a file by using this NumPy save text function. I'm going to say NumPy save text. I'm going to give it a file name, and this is up to us what the file name is. It's called savedata.txt here, but you can call it what it is. This is what I'm saving, so this is this function that I ran up here, but it doesn't have to be this. I could just put in X here or Y here or whatever data set I want to save here. Put a header and a footer into it, and then a format here. So in here in format, I'm saying save, the first element of each entry of this thing here is going to be a integer, and the second element is going to be a floating point number with one number before the decimal point and four numbers after the decimal point. So I can specify my formats in here as well. I don't need to do this. This could be inferred from the data and I could leave it out, but that's certainly possible. And so if I run that, I can't see anything's happened here in Python. If I quit my Python, I can see that at the bottom here, there's a file here now called savedata.txt, which I created. We can see that it's put in a header, which is just the word data, and I could put some more stuff in there if I would. it's put in a footer, which is the word end, and a comment, a bash comment character, and then it's put in the 0, 1, 2, 3, 4, and you can see one number before the decimal point and 4 numbers after the decimal point. So I can save my data out relatively easily with Numpy. So I can also then load that data back in. Well, so I've quit Numpy here, Python here, so I need to reload my Numpy library. Give me a second. You can see the data which I saved out have now read back into Numpy and stored in an array. Now, of course, I've lost, before when I created that data, we can't see it now, but it had more decimal place here, and these were two separate arrays. This 1, 2, 3, 4 was an integer array, and this entries here are a separate array. So I've lost all that when I save my data, but I've still got it in a form where I can load it back up and play around with it. It's also possible to. There's also some more advanced functions which you can have a look at, gen from text, or save and load rather than save text and load text, which will do other things as well. So gen from text will let you play around with skipping headers and skipping footers and those kind of things, and lets you sort of define a little bit more exactly how you're going to load text. Or load text into your data here. So there's an example in the notes here. You can see now that what it's done is it's let us skip the header, and it's skipped 2 lines on the header. And so I've omitted that first bit of data, and it's also says skip the footer, and it's skipped 1 line on the footer, so it's omitted that last bit of data there as well. So there's those kind of things you can do. And then there's the generic Numpy save and load functions rather than save text and load text. And they save data in their binary format rather than text format. So I could do, let me see if this will work. So So what I've done is I've used this numpy.save function and gave it a file name called savedata.dat and passed in the data I want to save. And if I look inside of that file, actually it created me something called savedata.dat.npy. It's created a binary numpy file. But I can't see any data in there because it's stored in a format that I can't access. And then I can potentially load that data back in using the numpy load function as well. Although this one's not working for some reason. Let me just check why that is. And you can ask questions as I look that up. Okay, so it was a good question there, Gavin. So going back a little bit, when I was doing the text stuff and I had the skip header stuff, where it said skip header equals 2, but it actually skipped 2 of them. Why is that? Well, actually, there are two header bits of text in that file. So if you look at the file again, in my savedata.txt, actually it has an actual header here, which is data, and then it has the first entry. So if I put skip header equals 2, all it means is skip the first 2 lines in the file. So it skips that one and it skips that one. The interesting question is why it skips one of the why it skips one of the extra things at the bottom where you say skip footer equals 1, and that's because it's automatically picking up that this is the end of a file. And when you say skip footer equals 1, it goes 1 back from where it's already found the end of a file, and so it knocks that one out as well. Does that make sense, Gavin? Okay, well, so I need to look a little bit more detail about the syntax of the actual load. I shall do that in a little bit. We'll not stick on this for too long. Okay, so you can read and write data, and in fact, actually, with the load text functionality and the load functionality, there's lots of nice things you can do there to, for instance, choose what your delimiter is. So you can load CSV files instead of load text. You can load CSV and choose a particular delimiters, and it will process CSV data into Numpy arrays. And there are various ways we can do that as well to get you access to data that's been exported from other places or collected from instruments and imported into Numpy. That's good. So there's also things we can care about in terms of, so if we're using Numpy and we're doing large data sets, working on large amounts of data, we may care about performance. And so it's possible to actually use this thing called timeit, which is a library in Python. So if I did import timeit, then I could do a particular timing of operations in Numpy. So if I did something like I'm taking a Numpy array, I'm creating the Numpy array with an A range and I'm reshaping it 10 by 10. I could then potentially play around with timing various sort of operations to that array. So give me a second to again look up the particular syntax of this rather than the As I say, it's always slightly embarrassing going off script when things don't quite work correctly. Okay, it's slightly more involved than I remembered. Okay, so we can use this time it. Apologies for the delay in working that through. We can use this time it library here, which is a Python library, and a time it function from it. And then I can say, okay, try running this 10,000 times, just accessing this individual element of an array. I have to use this lambda function here to say, actually, lambda means run this as a small function, standalone function, because time it expects you to pass in either a string or a function that it can run. And it says this takes 0.008 seconds to run overall. Actually, I might want to run it more times to get a nice reproducible number. So taking about half a second to run this now. And then we can look at things like, well, okay, does it make a difference if I access this in a different way? So accessing my Numpy data in a tuple rather than using square brackets, does that make a difference to the performance of what I'm doing? Actually, we can see it looks like it does. Now, of course, this is not a brilliant experiment because I'm running the login nodes and there could be various fluctuations in the compute resource I have access to doing this. And so you can see that if I use my square brackets for this two-dimensional array to access an element, it's taken around 0.5 seconds to do that 10 million times. Okay, so each one of those entries is going to be pretty quick. And it looks reproducibly about 0.5 a second. It's not terrible in terms of variability. If I then go to the tuple method instead of a double square brackets method and run it, then it looks like it's reproducibly a bit faster than that, but actually more like 0.3. You can see actually the way we use NumPy has got some performance implications. So the tuple method of accessing the data is actually faster than the non-tuple method of accessing the data because the NumPy library has to do a set of operations in one way versus a separate set of operations in the other way. And so that impact performance. I see Gavin's asking me if this is a known result. Yeah, I think it's pretty well known that the people method of accessing the stuff in NumPy is faster than the square brackets method is. Or at least hopefully it's well known by you people now, because I've told you. I think in general it is pretty well known about that kind of thing. So you can do similar kinds of things with different kinds of operations if you're interested to see different ways of doing things. So the other example in the lecture notes would be to say, let's see, we can create a large array. So X should now have 1 million entries. Or 10 million entries, my maths is terrible. And then I can see that X times X is the same as X times 2. So is times an array by an array different to squaring elements of the array? In terms of performance, both give the same answer. In terms of performance, they do different things. So again, I can use this lambda function here to say X times X. Do that a large number of time. How long will that take to finish? Actually, I may have been over ambitious by putting in 10 million operations there. So let's bring that back to something more like 100,000 operations and see how long that takes to finish. I may have even been far too ambitious. 100,000. Get down to 100. There we go. Okay, it takes about 1.25 seconds to square the matrices by terms in one matrix by the other, reproducibly somewhere between 0.2 and 0.3. Let's say 1.2, 1.3 seconds. Do this 100 times. As we can see actually that doing the same operation but going through and squaring each element individually seems to take longer. And that's because there's some level of vectorization that's going on in the underlying functionality, which has been optimized a bit more for matrix times matrix operations compared to individual matrix times make individual operations on the elements of those matrices. So both of these ways of doing it produce the same result. One may be faster than the other. Now, we don't discuss these things here because you should care about them too much. We just discuss these things here because if you start using NumPy heavily in your applications, it may become a point where you've written a code and it takes quite a long time to do something, process the data to produce your results. And that's the point where you start getting to actually I want to do some optimization of this Python code, and a sensible place to start is profiling the Python code. And if you found out that, okay, some of these operations like squaring a matrix, which is taking a long time, how do I work out a different way of doing that? Are there different functionality I could use? Can I time it and work out where performance is being spent, and is there better ways of doing it? And this is a method of doing it. So I don't expect many of you to require to need to do this day to day if you're using NumPy. It's just useful to have this reference material as a reference to come back to and have a look at. If you do find yourself in a position where NumPy is something you're using heavily and performance is suddenly an issue for you. Good questions, Gavin. I'm sure there is a sort of list of tips like these to write fast Python. I'll look one out for you. I'll look the sensible one out for you and get back to you. It's off the top of my head, I don't know exactly which is the best one, but I will look out a sensible one for you. Yeah. Okay. So that's all I wanted to say in terms of NumPy material. There's a lot more the library can do. Unfortunately, the online documentation is pretty comprehensive, so you can go and have a look and go through that stuff. And we actually do a scientific Python course, which is a bit more involved than this, which includes SciPy and some more things than that. So if it's something you want to end up using in anger, then it may be worth keeping an eye out for that course, particularly if it's online again like this one, so you can jump in and get some of the more in-depth stuff that we do there. At the end of the exercise, let me just stop sharing this screen here and share my web page instead. Yeah. At the end of this, what we've been looking at here today, there's a bunch of exercises you can do to have a look at putting NumPy into practice. Okay, so it's an exercise which is, can we estimate the area of a circle by throwing darts, collect the number of darts? So it's, generate a sample size, create a random set of x coordinates and y coordinates, count the number of where x times squared plus y squared is less than 1, and use this to compute an approximation to pi using this formula up here. And then there's a couple more, there's a solution there, a couple more on polynomials and calculating and things like that there. So if you would like to have a look at these exercises and get a bit more hands-on with running NumPy in practice, that's absolutely fine to do. You'll see here that there's some stuff here which says there's a solution for this darts exercise. So if you start doing this, calculating pi by throwing darts and run into problems, and that's after the session and you can't ask questions, there's a solution to it. But of course, because we're not running this as an actual IPython notebook, you can't see that here. What you actually have to do is go back to this core NumPy folder where the NumPy notebook is, and you'll see that there's a darts Python script there with a solution to what you need to do. So if you do run into a problem, it's there. But you can have a look at that. And then let's have a look. Yes, so there's a couple of more things to do, and the polynomial one actually has the solution to it in the notebook as well, so you don't have to look elsewhere for that. So if you want to have a look at those, that's perfectly fine. If you want to ask any questions, then do shout at me now. Otherwise, what I'll go on to do is talk about MPI for pi in the next sort of 10-15 minutes before we finish at 4 o'clock. Because we haven't got access to the system still, then we won't be able to run any Python there. So it's going to be much more me just talking through the sheet rather than me showing you anything running, because I can't run anything at the moment. So it shouldn't take that long. But anyway, but we can come back and look at it at another time if that's useful. Probably likely, I mean, I don't know the background of most of the people here. It's probably likely that NumPy is something that's going to be more useful and usable to you in the stuff you're doing at the moment compared to something like MPI for pi, which is much more about a sort of advanced parallel programming and using resources beyond a single compute node on something like Archer 2. So as I say, do drop questions in if you have any, but I'll just breeze through this as we go, so we understand what's going on here as well. So MPI for pi, message passing with Python, is a Python library, Python package, which provides interface to the widely used MPI library, which we use in parallel computing to write parallel programs which use more than one compute node. The MPI means message passing interface, and it's a way of being able to have workers on different bits of computing hardware connected by a network, and they all send messages to each other to do the parallelization. Okay. We have it installed on some of our big systems, like the Cirrus system at EPCC or this Archer 2 system, which you have access to now. But if you want to install it yourselves, you could easily do that on your laptops and things. You want to install MPI for pi, but you also need to install an MPI implementation, something like OpenMPI or MPitch to do. Okay, and there's details on how to do that in this web page here. The MPI for Pi interface follows the C++ MPI interface, which has this idea that you get an MPI object, and then you have the name of the function that you call from it. Okay, so how do we use this in practice? Well, you import the library, so import MPI for Pi. You can call it, so from MPI for Pi, import MPI. Okay, and then we can have this. It has a built-in thing called a communicator. So if you know about anything about MPI, the communicators are sort of groups of things that work together, groups of processes that work together. And the standard one for MPI is something called MPI COM world. And that means all the parallel processes that are working in this application at the moment. Okay, so when I do from MPI MPI for Pi import MPI, that sets up the MPI library for me, and it gives me this communicator, this global communicator, and then I can use that to do things like tell me what rank my process is, which is, what is the ID of this individual worker that's running, and how many processes am I running overall? So how many individual workers am I running? And that would be a function mpi.comworld.size, and these capitals matter here, right? It's case sensitive. I can say, here's an example where we've defined a main function, we pass in a communicator to it, and inside there we ask the rank and size, and then we print them out. And then you just call that as main mpi.comworld, pass in the communicator, and away we go. And so this here does the job of setting up the MPI library, and then here we're using it. But of course, we're not sending any messages here. We're just doing a MPI run. If I was on Archer 2, then I could actually run that using something like srun -n8 python example1.py. If I put this into an example1.py file, that would take it and it would run it on the compute nodes using 8 processors, and I'd have 8 workers that ran this out. And so each one should print out hello from 0 of 8, hello from 1 of 8, hello from 2 of 8. Of course, that's not that useful by itself. Really, we want to be able to send messages backwards and forwards with something like MPI. So this is how the workers individually communicate with each other. And so we have these functions send and receive, which let us do that. And so the generic send and receive functions are look like this, where you have to pass in, well, the first argument is a communicator, but we ignore that, so that's themselves. We pass in the data we want to send, the rank of the process we want to send to, and any tag we want. And then if we're receiving data, we say where we're going to put that data, who's going to send it to us, what tag do we want to use, and do we care about this kind of stuff. And if you're used to MPI programming at all, you'll see that some of this looks different from normal MPI programming, because Python has a set of defaults it provides for some of these things, so you don't necessarily have to pass them in. So it doesn't let you, it means you don't have to check the status of a message and things like that if you don't want to. These are specific capital S and capital R, send and receive. So again, the case matters. These are what we call buffered sends and buffered receives. Actually, there are, if we go slightly further down, there are different sends and receives we can use if we want to send Python objects rather than individual bits of data. So here, this will do what we would think of as like a pickle-in send and a pickle-in receive, where it takes a whole Python object, packs it up into a buffer, and sends that, and unpacks it at the other end. So you get a full object at the other end. Whereas these capital S and capital R send and receive are much more just send the data out of here and receive the data into here. Don't send all the functions and associated setup with the object. We don't have to tell it how many things to send, because it in general it picks up, okay, this buffer is 10 elements big, I'll send 10 elements. Okay. If we're doing programming with something like Numpy, we've got two multidimensional arrays. For performance, we may definitely want to send contiguous sections of data. This means data stored in the same consecutively in memory. And we can do that with Numpy arrays, where we can pass in this sort of buffer with extra functionality here. Tell it what we want to send. So we can actually say send a sort of contiguous chunk of data from this buffer with this many elements, and this is the data type we want to send. And so that definitely, we can do that sort of contiguous send and receive as well. So here's an example of a send and receive between two processors. It's been set up to run effectively on two processors, where one with rank 0, so our first worker creates a message to send, which is actually a 4-element array, all with 1 in it, and it uses this. You can see here this is a synchronous send. If you don't know MPI, then don't worry what that means, but there are different kinds of sends you can use, and here this is a synchronous send. I'm going to send this message here, this Numpy array, to worker 1 with a specific tag. And tags are just used to specify your message, differentiate between different messages. We don't have to use tags. We could set all our tags to 0 or not passing a tag here, and it would work perfectly fine. And then on my next worker, it's going to be the receiver, where the destination was 1, the rank was 1. I get a buffer, I get a data structure ready to get the data, and then I receive that data from my first worker and put it into that buffer. And in the end, once these two things are finished, the data that was sent here will now have ended up in this buffer over here. Of course, here it's not that interesting, because all I'm sending is a bunch of 1s. In reality, you'd have proper data here being sent and proper data being received over here. So if you have done any MPI programming before, it doesn't look that similar to normal MPI programming. It's just that some of these extra parameters need their names specified, and you don't have to specify everything you normally have to specify when you're doing MPI programming. There is functionality for non-blocking messages as well, so you can do I-sends and I-receives. Again, if you don't know MPI, don't worry about this. But if you do know MPI, this effectively is the same as non-blocking MPI, I-sends and I-receives. And the requests are returned from the function calls. So we can see that we've got these request types, request variables here, and then those request variables have a wait function associated with them. Again, if MPI is not your thing, this is detailed, you don't need to know. If you are doing MPI stuff, then you can see that we've got individual non-blocking requests, which we can call a function wait on, or we can use this mpi.request.waitAll and pass in a set of requests as well. And so that's also possible. So there's a class function which like a static class function which will do that as well. And so if you do message passing at all, you'll know there's also a set of functions to send data or communicate data between different workers, which are not just point-to-point messages between individual workers, but are collective operations as well. So collective communications, that means it involves everybody in a communicator, i.e. all your workers. And you can see in here there's a whole bunch of these which are supported, such as broadcast, reduce, and then the standard ones, which will be sort of all reduce and all to all and those kind of things. And again, as with the send and receives, we've got uppercase broadcast, which sends data, and lowercase broadcast, which sends Python objects. The same with uppercase reduce, reduces data, lowercase reduce, reduces Python objects. So those functions will work as well. So here's an example. You'd want to send you'd reduce your data, your com rank, and you would get that across all the functions, all the processes that are working. And finally, excuse me, the MPI for Pi also gives you functionality to do different communicators. So you can take this MPI com world and split it up into different communicators, just like you would in normal MPI, with things like MPI cart create, and MPI get rank and shift and those kind of things there. So again, if this is a kind of programming you're doing in normal MPI and you want to do it in your MPI for Pi, or you just learn MPI, these are some of the functionalities you can see. But the real difference is that we get objects with functions that we can call upon those objects, and then there are some subtleties as to whether you send in data or you send in obts, and that will make a difference. So there's a bunch of standard functionality in MPI for Pi 2, such as MPI W time, user-defined types, single-sided communication, MPIO functions. Not everything is 100% implemented, but the majority of stuff you'll ever need is there. So yeah, there is the only thing to be aware of in terms of performance is that quite often when you're using large numbers of processes, importing libraries can take a bit of time. So there's ways you can get around that, but it's sensible to have a look at that if you're going to run up to 10,000, 20,000, 40,000 Python processes running in parallel, then it's always worth looking at that. And there are things we can do there with containers and similar functionality, or copying data to file systems, which will improve that speed of import. It's a well-known issue in Python on high-performance computing, not just the MPI for Python, but in general. If you want to run, 1,000 Python programs all doing the same thing separately, it may take a long time to import stuff because it's all loading the same files from the file system. Okay, so that's all I wanted to say. I know it's a very whistle-stop, very high-level entry to MPI for Pi. In reality, if you're not an MPI programmer, then none of this will make any sense to you anyway. But if you want to play around with it and have a look at how it works, then once we get the system back up and running, as I say tomorrow, you can have a look here at running some of these examples here. So you could take an example like the example 1.py text at the top, put it into a file, take this batch script, and then run that on the compute nodes and see what actually happens. I have to thank my colleague Holly for doing a good job of going through and setting up all these batch scripts for the new Archer system. But these should all work fine. So there's a couple of exercises you can go through here to have a look at how you do MPI for Pi on Archer 2 and how you do MPI for Pi in general. And as I say, what you can do is come back. Once we tell you the system's available, have a play around with it, and then if you have any questions at that point, then drop me an email or drop us a line and get around. And so I'll stick my email here. So if anything comes up about NumPy or the MPI for Pi stuff that you don't want to put in the messages here, or if you want to contact me directly, that's perfectly fine. Please do. And I'm happy to take questions now, but if not, I think I'm done lecturing. Thanks for coming along. I don't know if Juan wants to say anything as well.
No, just to say thank you, Adrian. Yes, thank you everyone for attending this course.
On Arch before the account is closed. Absolutely. I'm not sure what the actual deadline for the account on Arch 2 is, but I think it'll be at least a couple of weeks. They should be open. Juan may know differently.
The account are really close. I think the third week of December. So I think it's the 19th of December is when the account closed. Also, if you have any questions or any comments, as I said before, you can use the collaborative pad. Yes, also the follow-up session will be 15th of December from 3 to 4 p.m. So then you can ask questions there and you can